buckets per level?
Yeah, the optimum number of buckets depends on how you build it. So you have to weigh that. So if it's 256 buckets, then of course each jump will be a full byte. So it will be half as many jumps to get down, because it's actually 8 bits for each jump. So yeah, the lookups will be twice as fast, but you will need 256 buckets on each level. So that would be, anyone have a pocket calculator?
Square.
It's times 3 there, so it's 2.5 levels. Let's say 3 levels. If we use 9 times 256, well, that makes about 2,000 node systems you need to keep track of. I think.
So that's actually not much information.
Well, I consider that too much, because
keeping it up to date.
Yeah, because that means you have to keep 256 buckets fresh on each level. That's a hell of a lot of communication.
Oh, right. So when you're walking, you have to find out too much stuff.
Yeah.
Yeah.
And then you couldn't transfer that with your random walker, because that would be every bounce 256 addresses, and each address is almost 100 bytes. Because it's a hash, some hash sums and IP numbers and stuff.
Right.
So, but you can manage that if you do it. If you actually learn of the addresses over these links, over the fixed links, because then you need to, at first when you connect to someone, you get 256 addresses. Then it just gives you the changes. When some of them falls away and there's another one closer, then it's manageable. Then I think my calculation said that 256 buckets was about right if you do it that way. Yeah, I think that in that case it was between 200 and 300 was optimum, so of course I chose 256 because that's 8 bytes. 8 bits. So in that case, yeah, but then it's static. But of course, it might not be a bad thing, because when you start jumping down, you don't have to start from yourself, you can start from someone else and go down. So each time you try it, you can use your random walker, of course, gives you new node addresses within this one. You can start, instead of starting from yourself, you can start from that. But that means an extra question. You have to ask him for a subgroup. So that means 1 jump extra, but at least then you don't get stuck. So I don't know which is optimum.
Sorry, did you mean that you would instruct the next level down's walker then to go out?
No,
Like, because you're saying you don't have to start from yourself.
First, here, what I mean is, if you usually when you jump down, you don't ask anyone, because you already have your buckets on this level. You already know 3 nodes for each sub-level.
And they're fresh.
Each subgroup, and they're fresh. Yeah. So you can simply look in your own bucket, one of the buckets. Well, if you want to go down to subgroup 15, you just look in your own bucket 15 that you're handling, and use those 3 to go down there. And if those 3 are all malfunctioning, then you won't get an answer. All those suddenly went offline. Then you have to simply ask someone else in this swarm, can I get 3 nodes for group 15?
Isn't that what your random walker's doing anyway?
Yeah,
just wait for the next top and you'll get another fresh node to try.
Yeah, if you have 16 buckets, then you can do it. On the random walker, you can get all 16 each time. But if you use 256, then that's too much data to transfer over the random walker. Then you would transfer it over those fixed links instead.
So what determines which bucket you end up in each level? Like what makes it an F or a C?
Well, it depends on what you're doing. For instance, it depends what kind of what this routing overlay is used for. For instance, if it's the mother net and the for instance, if it's on from the mother net looking up the engine form application, then what you're looking for is is actually the address engine form.
Yeah.
Or of course, it will be engine form plus the hard-coded password hashed.
Yeah.
So the address will be the hash of that. So that all the engine form nodes will be at an address that looks, for instance, like that.
Ah, okay. Yeah.
So you will jump down and routing overlay here to find the engine form nodes. But note that that is not a distributed hash table, because those nodes, when you reach that address, the nodes are actually there. You don't need to then get some information on where to get those nodes or get those files. So this is just the routing overlay, without any storage. We don't store anything in the routing overlay, well, except for the nodes themselves.
So,
So that one might be one thing. No, yeah. Was that?
Yeah.
Was okay.
the mini groups are fixed size to
Yes.
1,000.
Well, yeah, they could be like that.
So, obviously you can't just have a fixed length of, well, a fixed depth of tree. If you've got more, like you're limited to 1 million there, what happens if you get 2 million? Then you have a dynamic depth, or?
The maximum depth, because this is usually a SHA-1 hash sum. So the maximum depth here is 20 bytes. That is 40.
So does the depth, like you've got 5 there?
Actually, you have more. You have the hash sum is longer, so you have a long.
So you always have the SHA-1 depth number of.
Yeah, that's the maximum. But if you hash two different things, you will never get a collision that deep. That simply doesn't happen. It's too unlikely. But of course, if you're lucky, they will collide fairly deep down. And then you actually have to have all the levels down there to separate those two nodes.
Okay.
Is that okay?
Yeah.
There are some optimizations then when it's just two addresses that collide, but that's cheating.
It's a lot of traversal if you've got that many layers, just to find something that you're after.
But it's fairly quick.
Okay.
Because if it's a 1 million nodes, normally it's just 5 lookups, 5 questions. So you do it in like, since you can send 3 ask 3 at a time, the fastest one will respond. So normally you perhaps get a response within 50 milliseconds. And that's the.
Oh, I see. So you're still looking for the full hash,
yeah.
but you can
But
get
it will
to any
finish when you
depth.
reach the level where they are unique, where you only find these nodes with a full address.
Okay, so you are at each level. You're saying I'm looking for this.
Yeah,
Are
you
you
always tell
that?
what you're looking for, the entire thing.
Okay, so you might get to the second level, and
If
I'm
you
the only
like,
F0
when you ask
prefix.
here, perhaps you were actually expecting to do file out, but if you like, you actually bounce into one of those nodes
Right.
over there and said, I'm one of those.
That makes sense.
If you're lucky, that means one level up from what you're expecting, you might already start bouncing into it.
So when the request or the thing that initializes the route to start happening and you're looking for this hash, how do you end up getting back? How do you what do you end up sending back?
Actually,
You're looking for the node itself. So
we don't send a message down anymore. That's what they did 13 years ago in these hash tables. But if you send a message down and get it back up, it might disappear along the way. So instead, we're actually connecting to them, talking to them, and then we're connected to them and talking to them. So my node, who is looking for something, actually connects itself down the tree like a random walker almost. It walks down the tree.
and then you find what you're looking for, and you're connected to it. That's it.
When you find what you look for, you're actually connected to the node you're looking for, and now we're connected.
Okay, so you connect to the first one, and then it says you should connect to this other one,
Yeah.
and then this other one says, well, you should connect to this
Yeah.
one, and then now you're connected to the one that you want.
Yeah.
Okay. I got it.
It's a cascading connection, essentially.
Sorry?
Cascading down the tree.
Yeah.
Yeah, that makes perfect sense.
There's of course some optimizations to handle deep collisions and like that, but that's.
Okay, I misunderstood. I thought you were talking about sending the message.
No,
Yeah.
we stopped doing that like 10
Yes.
years ago
Right.
because it
Right.
wasn't efficient.
Yeah, that makes sense.
As I showed you, Cord was doing that.
Yeah,
But as you know on the internet, if you send a packet, you don't know who reaches its destination or if you get it back.
yeah.
So it's better to actually traverse down, actually connect yourself down. I don't think we have time for that, but we could talk about deep collisions if we have time later on. What should I say about this? Yeah. As I said, in a distributed hash table, you find a node that has that address, but normally you're not after talking with that node. Instead, you get some data, for instance, a pointer to a file that has that hash, and then you talk to the node that actually has the file. I think, is that clear for everyone? That in the distributed hash table, you store small pieces of database fields. Yeah. So that's the difference. The thing is, if you, like here, you're actually looking for a node with that address. You don't need to, the one responding and actually taking part is a node that actually want this address, want to be that address. You can trust that node that it will actually be honest in routing overlay because it's actually wants to be connected to on that address. It won't lie about its own address. Of course, unless it wants to infiltrate that swarm, but that's another issue. Yeah. Throwing effects, as I call them. If we have a big swarm like this, and most nodes are, for instance, we just, the mothernet and the application subnets, for instance, there's just a handful of applications, say just 4 applications, that's all, because the system is new. They will exist under 4 different of those, unless they collided, perhaps 2 are on the same, but then they're unique. Several of the slots will be free. Then suddenly someone makes a new application under a new name, and this slot will start to be used. Then you have like one node here that's announcing, I'm F something. And there's a million nodes here with lots of different addresses. If you have primitive algorithms for this, that one will get enough visible, because some other F node might connect over here. And they want to find each other to connect into their application swarm. So we have to do the broadcasting here the right way, and that's, as I was talking about, the slotted broadcasting. Like these buckets, they are slots, or buckets. Okay, buckets is good. So we will, whenever we bounce into or we spread over these links, we tell about each bucket. No matter how far away it is. If that's the only one available, it doesn't matter if it's 20 jumps away. It's still the other one. That's the one that everyone will see. So this one will actually be visible over the entire network. So this new node, that's at the same time we connect, will immediately from the neighbors here learn about that node. The first second it knows who to, and then they can connect together and go down and build their branch together.
What happens if you are looking for, say, an F, and you don't have one in your list, and you ask, your random walker?
There is no F, you mean?
Yeah. Well, what if? There might be an F, but it's propagating. It's in the process of propagating. Do you retry?
Yeah, of course. Actually, basically you don't retry because you will start working here, and you will place yourself there because you're also an F node in this case, perhaps.
Okay.
So if you're actually an F node, if you're just looking for it, you will just wait and retry. Mm-hmm. But if you actually are an F node, you're actually an engine form application or something, you put yourself there and start announce yourself as that, and over time, suddenly in your backend, when you connect to someone, you will get an address to another F node some minutes later, because, for instance, both of those connected at the same moment in time, as you said. After some minutes, like 10 minutes, the broadcast from both will propagate and they will see each other. And then they will, there's another one, they will connect down here, because suddenly, then this swarm will kind of repair itself and connect together. Because at the time both were down here, that's like 2 seconds, 30 seconds after both connected, they don't know about each other. So anyone here looking for them will just find one of them, perhaps. But some minutes later, they will figure out that the other one exists, and they will connect. And that swarm will then have repaired itself, so to speak. Do you understand that? Yeah. That's actually the answer to your question yesterday. If you have had a net split, because of America went offline or something, disconnected and Atlantic cables. Once they connect and you have this single node that you through start lists find 2 different nodes on each side, it will start, when it jumps around on one of the sides, it will start, if you do this correctly, it will start to broadcast data in both directions. And then the nodes here will start discovering each other and connecting, and then that will trickle down. So one single node connecting, if you do it in the right way, it will take like 10 minutes, and both distributed hash tables, both routing arrays have merged totally, if you do your algorithm right. That's also a reason to not have this static buckets, to have instead of use the random walker, because then you will constantly learn about new nodes for each of your buckets. And then after a while you will get them both sides, if you do it right. So you can make the 2, they merge automatically, and they don't notice it. They don't even know that they are merging. It just happens.
Do you have an algorithm to detect when a split has occurred? Or you just use the nodes online to do that?
I do it in my simulations, but I wouldn't use that in the real world. But in my simulations, I simply run my network for a while until it perhaps splits. Then I insert a broadcast in one node.
Right.
And let that broadcast go to the entire network because it's only one broadcasting.
Yep.
So, and then after a certain number of rounds, that where I normally would have reached the entire network, I check the whole. I just go with one loop through all the nodes and check if every node has gotten the message. If not, we have a net split.
Yeah.
But in the real world, can I detect it?
Because I guess there's some applications where you would want to know
Yeah.
the difference between.
Well, the net split really means if from those points of node view, it just means those nodes went offline.
Yeah.
It means you
So if a large amount of nodes
disappears
statistically
suddenly.
disappears, then
Yeah, if it goes from 1 million, you have the counter of the size of the network. If that one suddenly falls to 1 million nodes, there's a 500,000 nodes. You can, at least the human who looks at it can say, wow, 500,000 nodes disappeared in like 10 minutes.
seems like a
But you're aggregating those numbers over an hour though, so it wouldn't be.
Yeah, it would take an hour
It's a
to really
resolution
make
of
it
the RAM
visible.
as well.
Yeah, but still, normally you don't get that kind of fast change.
Yeah.
It shows from 8 o'clock in the morning to 8 o'clock in the evening you get that kind of change, but not over 1 hour. It doesn't dips like that. Not normally. So, but that's not a secure way to detect it. That's just based on an insecure number, the number of nodes. We don't know if it's a true number. So I don't know if you have. I haven't had a need to detect that, by the way. Really.
I was just curious, really.
Is it? Sorry?
I was just curious.
Well, you could use a random walker and check what continents you hit, because you know what IP numbers are which continent. And you can keep track of that and know that normally 5% of the time I hit South America, 50% of the time I hit North America, and 10% of the time Asia. And if suddenly one continent isn't responding, then you know it's gone.
Yeah.
But then you don't detect small nestlings that just detect if a continent disappears. So I think it's hard to detect small nestlings if just one island disappears. The big group will notice that.
Yeah.
The small group will of course notice that, because everything just goes crazy.
Yeah.
But yeah. Good. To get this merging effect to happen, you have to design your how you connect the routing random walker correctly. And I don't remember how to do that in the kind of network that we have used as an example here, because I use something else that is very different. So we don't have a day to explain that. One way is, of course, to use 2 random walkers. When you start to find 2 nodes, you start one random walker from each of them for a while. And then after a while you can just throw away that one of those random walkers. That would be one way to cause these things to merge. Oh, well, sorry, I don't remember that part now.
Speaking of routing, you are relying on internet service providers, right, for the whole infrastructure?
Yeah, most modern peer-to-peer networks are overlays on top of the internet.
Yeah.
So we call them an overlay. So yeah, we expect that the internet is there and functioning at least reasonably well.
Yeah.
You can reach most nodes, not all nodes, of course, because random networks can handle even if you can't reach everyone directly from your node.
Yeah. Yeah. So, would this have to change drastically if you just said like every node has its own Wi-Fi hotspot and that's it?
That would change it drastically.